Hi, in this video I'm talking about how to write a molecular ionic and net ionic equation using the special case of an acid-base neutralization reaction that includes sulfuric acid. And H2SO4 sulfuric acid is a special case. If we look at the table of strong acids here, sulfuric acid is different from everything else in the table because it is the only polyprotic, specifically a diprotic, meaning 2 protons, acid on the table. It's also different from all of our other strong acids in that it has 2 ionization reactions. So ionization is the process by which molecular compounds such as acids and bases can turn into ions in solutions, making them electrolytes. Now, only strong acids are strong electrolytes because only strong acids ionize completely, and we show this using an arrow that goes one way, showing the ionization goes to completion. Sulfuric acid, because it has 2 protons that can come off, they come off one at a time, so there's actually 2 steps to its ionization. And if you'll notice here, sulfuric acid's second step of ionization is a weak ionization. The arrow goes both ways, meaning it, at the end of the day, stays mostly over here on the reactant side and not very much of the product is produced. So if we just had this ionization going on, it would be a weak electrolyte. But because the first ionization happens to completion, sulfuric acid is technically a strong electrolyte. But this will come into play when we write out ionic equations. So let's look at the example problem here. Write the net ionic equation for the reaction of sulfuric acid with potassium hydroxide. So this is an acid-base neutralization reaction. So it's asking us to write the molecular equation first, then the ionic, and then the net ionic. And I've already written them out for here, but I'll show you how I got to this. So first of all, when I react any acid with a base, the products are always water and some sort of an ionic compound, where the water came from the hydroxide of the base and the protons or hydrogen atoms found in the acid. The ionic compound, therefore, is the anion portion of the acid with the cation portion of the base. So in this case, potassium is my cation and sulfate is my anion. So we end up with potassium sulfate. Potassium is a +1 ion, sulfate is 2-, so potassium sulfate would be 2 potassiums to every sulfate to cancel out the charges. Once we balance that equation, we would take 2 potassium hydroxides and produce 2 waters. So there is our balanced molecular equation. Everything's aqueous except for water, which is a liquid. Next, the ionic equation. Now this is where it gets tricky because in ionic equations, strong electrolytes break apart into their ions, while non-electrolytes and weak electrolytes are left as their molecular compound. So in sulfuric acid, only the first ionization happens strongly. So instead of it breaking down into hydrogen ions and sulfate ions, they're actually going to break down into hydrogen ions and hydrogen sulfate ions. Only this ionization happens strong enough to appear in the ionic equation. Potassium hydroxide is a strong electrolyte because it is an ionic compound, so it breaks down completely. Notice that 2 gets distributed to both ions, 2 potassiums, 2 hydroxides. Water is a non-electrolyte, so it stays the same. Potassium hydroxide is also a strong electrolyte because it's also an ionic soluble compound, so we get 2 potassium ions and then 1 sulfate ion, and sulfate is a 2- polyatomic ion. Now to do the net ionic equation. To go from an ionic equation to a net ionic, you cancel out spectator ions, which are ions that are found on both sides of the equation. In this case, looking at the ionic equation, the only spectator ions that appear on both sides are these 2 potassium plus ions. So we're just going to go ahead and cancel those ions out. So once we've canceled out our potassium ions, what's left over is what's referred to as the net ionic equation. So the hydrogen ion stayed, the hydrogen sulfate stayed, the 2 hydroxides stayed, The two waters stayed and the sulfate stayed. So here is our net ionic equation.